Amy, thank you very much for the nice introduction. Dean Rutherford, thank you for the invitation, and I appreciate that you invite me for this honorable talk, and I will try to do my best to give the information that we know and possibly the information that we do not know about the seismic activity in the central United States and within the states. The announcement that came to you is related to the new activity in the central part of the state. However, I took the liberty to expand and talk about the seismicity within the state in general. So I will not only concentrate on the recent 4 or 5 earthquakes that took part in the central part of the state, but we will expand a little bit and give you some background information, give you about area that has the potential of generating earthquakes that poses risk to the state and also to the surrounding states. So what I will start my talk by going straight to the conclusions. Yes, so I will conclude the talk, and I'm going to come back to the conclusion again. And I really hope that by the end of my talk, that you are not going to be scared, but you will need to be prepared. This is the intention of my talk, not to scare the people, but to educate them to be prepared and be ready for a natural event that scientists still have very difficult time predicting. This is not a tornado that we can see it's coming. This is not a storm that we can see it is coming, or a tsunami that we can see and predict where it's going to be hit. The earthquakes are natural phenomenon that we cannot see, but we can predict only the location or the high possibility of the location. We cannot predict the time, we cannot predict the magnitude, and we cannot predict the outcome of these natural phenomena. We cannot predict it, but we need to be prepared. So to come to the conclusion, I will try to give you information to convince you that the seismic activity within the states, it has larger potential than many people think. Actually, the seismicity with the state is more active than many seismologists believe. Not just regular people, but many seismologists, they do not believe until we start showing them some of the recent results that we discovered. We will also talk about the source region that is currently being identified, and it poses risk to the state. We have within the states are 2 types of activities. Earthquakes are stress released that is going to be stored within the rocks. And the release of the energy or the release of the stress from the rocks in the form of earthquakes. Some of the release related to tectonic activity that's due to the plate motion or reaction of the plate to the external stresses where the energy is going to be released in the form of earthquakes. Some of this energy is released due to the hydrothermal activity. I'm going to show you these 2 examples because these 2 examples exist within the states. So due to the hydrothermal activity, that's water percolating from deep into the crust, coming up, propagate close to the surface, lubricate some of the cracks, and start moving the fault. So we have these 2 types. So we do have two of these types of activity within the state. Like I said, we are too far from predicting an earthquake. And many of the seismologists, many of institutions start concentrating on preparedness and mitigation and scale down on the issue of prediction. The Earth is a non-linear system. It's a very complicated, and there is so many unknown that is currently existed that we cannot put together and come up with a formula or with an equation to tell us when, where, and how big an earthquake is going to happen. So we are concentrating on designing the building, preparing roads and bridges such that they will stand an earthquake than predicting an earthquake. So we're a little bit far from earthquake production at this point. So what we need at this point is we need to prepare, mitigate, and also concentrate on public education and community outreach. We need also, in order to study this phenomena, we need to monitor it. That means we need to have number of seismic stations around an active zone to monitor the activity. This is not just to tell us that an earthquake happened. Many people think that a seismic station is a tool is going to predict an earthquake. This is not the case. Seismic station is not to predict an earthquake. It's only to monitor if anything happened. So it is after the fact. But when the data is going to be accumulating at the seismic station, and a seismologist like me, Dr. Mahdi, or Mr. Uqba is going to use, what the outcome of our research is going to tell us how the seismic wave is going to be traveling through the Earth, how much energy is going to propagate from one side to the other. And then we can have a scenario earthquake at a specific site, and we know what we need to design at the point where we need to construct. So it's not just to look at the earthquake after the fact, but the data that is coming out of it is going to use for engineering and also for designing purposes. So the monitor is very important. So is the research. Research is also important to give us information about what the earthquake is going to do for a specific site. What is the ground motion? And I'm going to show you some of these. How severity the ground motion is going to be from a specific earthquake at the specific site. And this is going to help the engineering community, it's going to have the preparedness community, it's going to have the mitigation community to design their plan and come up with the design that is going to stand an earthquake. Now, the last conclusion, philosophically, I said earthquake indicates something other than disaster. It indicates that the Earth is a living system. That means something inside the Earth is still generating force. That means within the Earth, there is something that is currently active, which is mainly the heat. That means the Earth is still alive. Earthquakes and volcanoes indicate that inside the Earth there is also some source of energy. That means the system is still alive. If you go to the moon, you don't see moonquake. If you go to Mars, you don't see Marsquake. You don't see them. That means the system is dead. There is no living things. That means within the Earth, that's the core, which is a melt, is generating magnetic field. It's saving our environment. If we don't have earthquakes, that means we don't have plate motion. That means the source of heat within the Earth is dissipated. So they do indicate something that the Earth is alive and good at this point. So it's not all bad at this point. Okay. Now, I always try to show this map when I do a presentation. This is a historic seismicity map. Before this map, this was generated by the late Professor Otto Nutley of St. Louis University, and he's one of our mentors. He went through all the historic records of the central United States and collect this information, and he started to compile these things and come up with this map. And this is the first map or the first database that was generated to tell us there is something at high risk in the central United States. Before this map, before the 70s when he started working, nobody knows what the New Madrid seismic zone is. Nobody knows there was a major earthquake that took place in this area. Very few people knew about it. But this map, and if you notice in here, there is a high concentration of seismic activity in this spot, and this is the New Madrid seismic zone. So this is the first map that alerts the people, alert the seismologists, alert the geologists, alert the public officials about the potential risk of seismic activity in the central United States. Now, this is a map of part of the central United States showing the seismicity. This is instrumental seismicity. That means each of these data represent an earthquake that is instrumentally located. These are not historic. This is by instruments. And this has been collected since 1974 because after the historic map, people start doing installation to seismic station in this area. So this is the outcome of the installation of instruments, seismic station, and we start. Now, this map is different than the other because it starts defining certain pattern of seismicity. We have this pattern, we have this pattern. Oh, I'm going ahead of my time in here. And we have this pattern and we have this pattern. These are group of faults. So the New Madrid seismic zone is not a single fault. It's a fault system. They zigzag each other. And this is what complicates the seismicity of the central United States. Now, we all know that California, they have earthquakes, the San Andreas Fault. This is different seismicity than California. Most of the Earth seismic activity, they concentrate into certain narrow zones. And these zones, they call it the plate boundaries. The Earth consists of many plates, 7 major plates. And most of the energy as a seismic energy released concentrate on the plate boundaries. Also, most of the volcanic activity, they concentrate on the plate boundary. This seismicity is not a plate boundary. It is seismicity within the plate itself. The North American plate extended from the San Andreas Fault to the mid-Atlantic. And this is seismicity that is within the plate itself. And people start wondering why we have so many earthquakes, some of them very large magnitude, that is not associated with the plate boundary. So I'm going to try to explain to you why do we have this group of seismic activity. Now, currently this is a seismic activity. Now, 600 million years ago, the North American plates tried to separate into 2 parts along the northeast southwest trend. The stress was the regional stress was extensional, and these are the arrows indicate the stresses that are extensional. So it's pulling the plate or it's pulling North America apart, similar to the current process in the Red Sea and the Dead Sea, where the 2 plates are being pulled apart. So the process started 600 million years ago. For some reason that is not within the plate, but external, this process stopped. It didn't materialize. During the process, water started flowing into this area and covered the whole area with water sediments, river sediments. Water sediments is going accumulated in this area. But what's left is the old faults that are due to the pulling the plate apart. So a group of faults that extended into the northeast, southwest direction, and many groups. But these are the two dotted lines represent the boundaries of these fault systems. So what's left only these fault systems. Now, from this time to now, there was many episodes of contraction and expansion. Stress regime changes. But what the current stress regime right now is compressional. This is what is currently active. Stress regime is compressional. That is compressing the two plates or the plate of the North American together. It's logically when you try to break something or stick, the easiest way to break air where it's the stick, its weakest point. This is exactly the same thing. So when you stress it in here, where it starts breaking at the area that's where the place at its weakest place, that is the wound, that's the old wound. These are the old faults. So these old faults start to become reactivated and start generating earthquakes because of the compressional regional stress that is currently active. So this is the main reason that we have seismicity at the New Madrid seismic zone. It's due to the compressional stress, and the old faults start to be reactivated. This is another map for the New Madrid seismic zone and showing instrumental as well as the historic. These red dots represent the three major earthquakes that took place during the 1811, 1812 series. And these are earthquakes 7 to 8 magnitude, and were calculated by the effects of them on the ground. We were able to determine their magnitude. So what you see in here, again, the seismicity of the New Madrid seismic zone, and also the three major earthquakes that took place. The one that extends into the market tree is one of the biggest earthquakes out of the three. So it is a source of risk in this area. Okay. Now, this is a map showing the Mercalli, or the modified Mercalli intensity scale, due to the effect of magnitude 8 plus that is going, hypothetically, if it is going to happen in this area, what is going to be the distribution of intensity? That means the amount of damage, the amount of effect on the state due to an earthquake of magnitude 8 plus that is going to happen in the New Madrid seismic zone. Now, keep in mind that this map considers only a source of a New Madrid seismic zone. It does not consider any other potential sources because they are currently unknown to many of the scientific community, and I will discuss some of these with you in a minute. This is what we call the ground acceleration. That's how much shaking is going to happen to the ground. And this is what engineers use for their design. So what is the severity of the vibration from an earthquake that is going to happen within a 50-year period within the New Madrid seismic zone in the central United States? We also have in Charleston, Carolina source, and we have another source in New York. But this is the major area is within the New Madrid seismic zone, and you can see in here the state is going to be severely affected by an earthquake of magnitude 8 plus within the New Madrid seismic zone. Okay, this is the distribution of, again, the same observation. That's the ground acceleration that is going to be distributed within the state. And if you notice in here, it's a very small variation for this line because it's only the area within the New Madrid seismic zone were considered in calculating these map. Now, I intentionally showing this because later I'm going to show you the same thing when I'm going to place another source zone on it. This is in here the peak ground acceleration from a scenario earthquake in this area of 7.7 magnitude. And this is showing you the severity of the ground vibration. And we're here in Little Rock, so we're still far away from it. But keep in mind this map because I'm going to show you again this map in a minute and showing you when we are going to predict or we are going to discuss other source region. Now, This is the return period for the New Madrid seismic zone. What's showing in here, that's a magnitude of 4 to 5, has a return period of 14 months. This is not prediction, but this is from the statistical point of view, from the statistical calculation to the history of the seismicity. This is where we come up what we call it the return period. That means the period between earthquake of similar magnitude. At 5, it's about a 12. It's about a 12-year. 6, it's about 9-year. And keep in mind, from 6.5, this is where we're preparing for, the 6.5. The last one happened in 1895. So we are overdue for an earthquake at the New Madrid seismic zone with a magnitude of 6.5 because the return period is 9, and we are almost 110 years right now. So we're due for one. I know you're scared, which is okay. 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 The 7 magnitude is somewhere about 500 years, and the 8 magnitude is about 1400. This is based on statistical calculation and the geology that we studied at the New Madrid seismic zone. Okay. Now, we went through the New Madrid seismic zone. What I'm going to go with you and showing you area, which is different mechanism of earthquakes. This is the Enola swarm, and some of you might recall in 2001 there was a group of earthquakes that took place in Enola. I'm going to show you what are these activities. I'm also going to show you an area in here that's, if you look at this one, you don't see any earthquakes, but I'm going to try to convince you this is possibly the second dangerous area in the state beside the New Madrid seismic zone. Also, I'm going to show you the area or discuss with you the recent earthquake that took place in November of last month. So I'm going to go in order of these things. I'm going to talk about the Enola swarm or Enola earthquakes. These are the map that was generated by the Arkansas Geological Survey. And you see the concentration of small earthquakes. Now, this is what I mentioned earlier. This is related to hydrothermal activity. If you remember the New Madrid seismic zone, there was a linear feature of seismicity. If you look at this seismicity, there is no linear feature. They are random. They look into almost as a circular pattern of seismicity. There is no single fault where the earthquakes align on top of them, not a single fault. But if you look at the seismicity in each of these that represent an earthquake, the seismicity is not going over a pattern or linear feature. Now, this is, I said, it's a hydrothermal activity. That means fluid propagating deep into the ground and then get heated and come back to the surface or close to the surface and lubricate the cracks, micro cracks, and the small fault in the area. If some of these faults are partially stressed and you put water into them, they will be lubricated. They will be much easier to move. So this fluid is going to lubricate the fault, is going to be easy to move, generating these earthquakes. Now, there was 2 episodes, I'm going to mention 2 episodes of earthquake sequence or earthquake swarm in this area in 1981, 82, and 2001. That's almost 20 years between them. I'm going to go with you, look at the characteristic of the earthquakes that took place in this area. Usually, the hydrothermal faults or the hydrothermal earthquakes are of medium to small earthquakes. They don't intend to be very large. So far, the hydrothermal earthquakes are maximum we've observed throughout the globe is about 5. In the Enola swarms, the maximum that we observed is 4.5 4.5 that happened in 1981. In 2001, another sequence of earthquakes happened with a maximum of 4.4. So they are comparable. So with continuous observation, it is possible that the return period of these swarms is 20 years, 2 decades. We observe 2 times. We observe it in 1981, we observe it in 2001. So it is possible that the repetition of this swarm is at 20 years. Now, the group of earthquakes that are is going to be very closely spaced, because the fluid is not going to propagate it throughout the crust. It's going to be propagating just above the area where the fluid is going to come. And they are also going to be episodically and close in time, not just in space. The earthquakes have no clear geologic structure, no faults associated with them, but they are randomly distributed along the area where the fluid is percolating. The activity is periodic, just like I said. It's going on. It's keep producing earthquakes, very large number of earthquakes, in the thousands, and it stops over a period of a year or so, producing this earthquake and it stops. It's still dormant for a couple of centuries, a couple of decades, and start all over again. And it sleeps and start all over again. So the activity of hydrothermal earthquakes are periodic, so they don't happen continuously. It's going to be happening every number of years or every number of decades. Okay. The seismicity of the Enola swarm is a typical of hydrothermal that's been observed all over the globe. Now, we also observed so far 2 episodes in 1981 with a larger magnitude of 4.5, and also in 2001 with a larger magnitude of 4.4. In the 1981, so far, the data indicates somewhere about 20,000 earthquakes that's happened. Very large number, but very small. In the 2001, the number of earthquakes, somewhere about 25. We're still analyzing the data, somewhere about 25 to 4,000 of them. But the majority of them are predicted by or recorded by instruments, not by human. Just a few of them were felt by human. But still, very large number of them, and the majority of them are of a small size. Now, this is what I'm going to take you from the central Arkansas, Enola, going into eastern Arkansas. And this is what I'm going to discuss with you. This is the new discovery. This is just some of the data that we will see we collected just this past weekend. Okay, some of the results has been published, but the majority of what you are going to see is still in the making. And like I said, just came back last weekend with some new result that I'm going to show you. The area, that's the new Madrid seismic zone, the area is here. So there is minimum number of earthquakes, no earthquake that existed in the area. Nobody knew about such area that exists. Now, being in the area and studying the area for the last more than 25 years, I always thought it just doesn't make sense that if the regional stress is compressional right now, why just this small part of the entire fault system is active? Physically, it doesn't make sense. I mean, if you look at these things, I mean, you see very sharp termination to the seismicity here, very sharp termination to the seismicity here. And these are background seismicity, they are not much, but most of the 4,000 earthquakes that happen in this area, it didn't make sense why the seismicity is not extended in this area, why the seismicity is not extended in this area. Because when you look at the regional stress, it doesn't come to a small area. It's come for the almost half or the entire plate. So there might be something happening that preventing the seismicity from propagating to the southwest and to the northeast. Or the possibility of earthquake in this area is migrating. This is the hypothesis that I'm trying to study and hopefully going to prove. That means the seismicity currently at the New Madrid seismic zone, as we see it, is active right now. But it's not going to be continuously active forever. The seismicity is going to migrate from this area, possibly to this area, in a few centuries or a few thousand years. And it possibly is going to stop and move somewhere else. So the entire region is going to be affected by seismicity. And this is where I start doing some work, all the way from Indiana and going to Illinois, going to Missouri, going to Arkansas. And in here, we find something that is possibly, it's going to tell us something that's a proof of the hypothesis that I'm trying to come up with. This is a satellite image that we examined before we went to the field and start collecting the data. Not many people think, so what you're trying to tell us from this? But if you carefully examine this satellite image, this is, Mariana is here, if you know what's Mariana. This is just the area that I was showing, the diamond in the previous map. This is this area, this is small area in here. So this is in here. And if you look at this area in here, and you see the ground is different than the area in here. There is much more disturbance to the soil in this area. If you look at these disturbances in here, in this area, in here, is much more than other areas. And this is, in a farming community, should be unusual. Why this area is being so disturbed? Why the soil is so disturbed, while the surrounding is still not disturbed? So we went to the field and tried to find out what causes these disturbances. What we're seeing in the satellite image? Are they something different or just normal things? So we went to the field. This is a low-flying flight. That's we chartered a plane and to start looking into the area, because sometimes you look at it from the low-flying plane is different than you look at into the ground, is different than you look into the satellite image. And what we found, very large number of such area. This is a cotton field in here, and we look at this area that's white. It's all sand, pure sand, medium grain sand that exists in here. And we don't know where it's coming from, why the sand exists in this area. I mean, the surrounding field in here, it's a clay, silt, but in here a high concentration of sand. And this sand is not like very thin area. Now, some area is steep, about more than 2 meter sand that existed on the surface. This is the sand in here. This is a cotton field. And if you look at this cotton field, this is the cotton in here, and all the cotton crop dead. They don't grow in this because they grow, not because this is poison or something, no, because the sand, it's thick, it's dissipating the humidity very fast, much faster than the clay. The clay holds the moisture. This is where you see a healthy cotton field. In here, because the sand, it's a coarser grain, the water dissipates. No matter what you water it, it's going to die because it's not going to stay in the soil. So most of the crop, they die. And you see in here, it's a fine grain sand that exists on the surface. So where is the sand coming from? It's a two possibility. It's either through river or lake sediment. This is a river, and you see in here, this is the San Francisco ditch and river, and this is a river sediment. It's either coming from the river, deposited on the surface, or it's coming from below. There's no other way that where the sand is coming. It's either it's being ejected from below, placed on the surface, or deposited by the water. So these are two possibilities. The first thing has nothing to do with earthquakes. But this, if it's coming from below, it has to do with earthquakes. This is what we call it sand blows. If we have a sandy layer that is confined by a clay on top of it, and a clay at the bottom of it, and you shake this sand very severely, it's liquefied. It's become jello. So if this liquefied sand is going to have a place where it's going to come eject to it, the load on it is going to press it, and the sand is going to be sand volcanoes. And this is where you see the sand is coming to the surface. So these are the only two possibilities where we see the sand on the surface in the Mariana area. Now, in order to substantiate these two, we have to do some innovative work. And what we did, this is a real example of the sand dike. Okay? In here you see this one schematic diagram, but this is a really sand dike. This is the sand in here. This is the silt layer. And the sand is being liquefied and ejected into this area. This is a very phenomenal observation. This is not schematic diagram. This is a real photograph in eastern Arkansas by the Mariana area. So it tells us something that's possibly that this area is being liquefied in the past by some shaking. And the most important aspect of these things, if you look at this sand area in here, and you look at this sand area, they are different. This sand is different than this sand. That means it is possible that this area is not affected by one liquefaction, but by several liquefactions. That means there is a repetition to the earthquake in this area. So this is an example. So what we did, we decided in order to verify, because when you look at the sand below, you don't know if it is coming from below or coming from. So what we did in here, we start taking a ground penetrating radar. That's an X-ray to the ground, similar to an X-ray. So we took an instrument. This is the instrument. That's the antenna. And Okba is doing the monitoring. And we drag this was on the ground to see if we can going to be able to predict if there is a fault or there is a crack or there's a dike that's emitted the surface, or if it is not, that means it's deposited from the surface. Okay? This is an area, a sandy area in the Mariana. And what we found in here, from this profile of the ground penetrating radar, that's the X-ray. This is the contact between the silt and the sand. And if you notice in here, there is a break in the continuity of this surface. You have the sand layer on top, and you have the silt below it. And there is a break in the silt below the sand. That means the sand is being emitted or erupted from below. This is a good indication that the sand is coming from below and it's not from the river. This is one. This is another example in the same area. And if you see, this is the three-dimensional image of the ground penetration radar. This is an X-ray of the subsurface. Okay? And if you look in here, there's another break in the continuity of the silt-sand contact. That means it is being affected possibly by a ground shaking. This is another example that's showing the continuity is being disturbed by the sand below. And this is a brand new that we collected in here. And this is a clear indication that the ground is being broken, and it's not a river was depositing the sand on the surface. And then what we did is we went to the field to verify the X-ray or the ground penetrating radar. So we did a trenching. And from the trench log, we collect sample to date to know when this event happened and to see what is the surface of this area is going to tell us, if it is going to be coming from below or coming from above. This is, I'm going to explain to you what is this. This is in here the contact between, this is the side of the trench that we dug. This is the side. And this is the floor of the dike. So in here we're looking at the wall of the trench that we dug. And if you look at this thing, this is the contact between the soil, the old soil, and the sand on the surface. And if you look in here, it's supposed to be continuous this way. But for some reason, this one dropped to here. So this area belonged to this. So what happened in here, if this is the surface continuity, what happened is this part is just open and a drop. So it starts telling us that this area was faulted. That means a fault that moved this part below this part, and the area moved in this direction. And this is what happened. That means it's not just a dike, but it's a fault motion that generated the existence. And the sand was erupted from here to the surface. So this part of the soil belonged to this part. And this is the old surface, and this is the new surface where the sand is going to be coming to the area. This is a schematic diagram of the side of the trench. And if you look at this one, this is continuous to here, and this one drops. So this part belonged to this part if you put it back together. So this area from here was dropped and opened, and the sand was erupted to the surface. So it is, again, the area was erupted in this direction. And then we said, okay, we kept surveying the area on a continuous basis and collect the data. And we put the location of the dike that was predicted as a fault. So this is one, and so on and so forth. When we put them together, it's a linear feature, and here's the fault. This is the fault that was taking place during a major earthquake. We requested from the United States Geological Survey to bring a special truck, they call it the CPT, cone penetrating test, to tell us what is the maximum magnitude that is going to liquefy the sand and put it to the surface. And they came and they did survey to the area. It's the cone that's penetrated the earth is reached until it reaches the sand, and it has some sensors that tell us what is required from the ground motion to tell us about this earthquake. And the result that came back to us after the analysis indicated that a minimum of magnitude 7.2, this is a major earthquake that took place in this area to create this fault. This is not a small one. So was at the beginning was scary, to tell you the truth, to know this, because nobody knew about it in the past. This is a brand new result. Then we wanted to go to the field and collect the data for dating, because it's not just, do you know an earthquake? Earthquakes everywhere, but you need to know when this earthquake happened. And also if there is a series of earthquakes. So we collected the samples. This earthquake happened 5,000 years ago. And 5,000, when you come to geologic time, is just a drop in the ocean. When you consider 4.5 billion years, the age of the Earth, and you consider 5,000, that means the fault is not dead. The fault is dormant, and it has the potential of reactivation. Now, we went again to the field and collect more data to see if more than one earthquake happened in the area. And there is one site that we're still studying. We were able to find 5 consecutive earthquakes that took place in this area over a period of 2,000 years, between 7,000 years ago to 5,000 years ago. Now, this work is still continuous. We're still doing research to see if more recent earthquakes that took place in this area. So we're still working continuously. But this is the map on earthquake. This is almost 7 miles long fault. This is only the surface expression of the deep fault. It is possible that the fault at depth is much longer, much wider, and it also extends into much longer distances. That is going to affect much larger area. This map is not by mistake, or this photo is not by mistake. This is, we took this photograph in the area that Okba brought to me this weekend. There is a major gas pipeline going through this area. I mean, this pipeline, you can walk into it, not just like pipeline. No, you can walk into this pipeline. It's a huge thing, okay? It's providing gas from the south all the way, all the northern states. The bad things that this pipeline is going through here and it crosses the fault. Yeah, it crosses the fault in this area. And during our field work, previous field work, and we went and we ran into some of those engineers that's running. He said, do you know there is a fault zone that's running it through this area and you're running your pipeline across the fault? And he said, what's that? He said, a fault that's been generating earthquake in the past. He said, I don't want to talk about it. This is his reaction. He said, I don't want to talk about it. Leave me alone. Let me finish my job and go. I'd have nothing to do with the fault in here. So this is the typical reaction from these people, but the pipeline, that's huge, it's running through here and it crosses the fault in this area. So these are some of the results of the new discoveries. I know time is running out, but I need to go into the recent research. These are a brand new source zone that has the potential of generating earthquake. This is the fault zone is almost 10 kilometers long. That is the 10 kilometer, that's the surface compression that we can find it. We're still working in the northwestern part to see how far it extends. We're still working in the northeastern part to see how it extends. And possibly we are going to ask for more seismic equipment to survey the area to see how deep this fault is as a fault, because this is only the surface expression of it. Now, from looking at the seismicity of this fault, it has nothing to do with the new Madrid seismic zone. It's a zone independent. It's by its own. It's generated its own earthquakes, and it's not related to new Madrid seismic zone as a zone itself, but it's a new source region. Okay. It has been extensively active in the past 5,000 years, and it has the potential of generating large earthquake in the future if the stress regime is going to be compressional again. The magnitude, the larger magnitude so far is more than 7. That is actually measured from engineering equipment, okay? We have not evaluated the risk of this fault. We're still working on it. And also we need to determine the return period. The return period is what is the time between two successive earthquakes of the same magnitude. We're still working on it. And we still need to do much more research in order to verify some of these information that we need to look at. Now, I told you to keep in mind this map before. And if you look at this in here, this is the highest area of ground vibrations, too far from Pulaski, too far from Little Rock. But if this earthquake is going to have the same magnitude as this one, 7.7, we have 7.2. It is possible more than 7. There's a minimum 7.2 in this area. But if you are going to extend this one in this direction, it's going to be, this is the closest, so this is the distance from here to here. But now, the distance of higher area of ground shaking is going to be from here to here. So Little Rock is going to be at much higher risk from this fault zone than the Madrid seismic zone. Okay? This is where I just placed this one. This area in here is the same area as this area. So it is much closer to Little Rock. So the risk from this 7.2 and larger earthquake is going to put us at much higher risk than the new Madrid seismic zone. Now, this is a schematic diagram. Many of the bridges in the East Arkansas, they have their piers sitting in the liquefied sand. We observe these things, okay? This is not, I mean, this is a fact because we know the depth is somewhere about 10 to 15 meters where the sand is being liquefied. It's coming from below. It's a depth of about 10 to 15 meters. So these piers are about 5 to 15 meters deep. This is the silt, the sand, and the surface layer. And if you put the pier in the sand and you shake the sand and this one become fluid, you imagine what's going to happen to the bridge, okay? It's going to have piers. These piers is not going to have shear strength. That means it's going to collapse. That means these piers is going to sink because nothing is going to hold them. It's going to sink. So many of these bridges also is going to have a problem. Many of large buildings is going to have a problem. So is the lifelines, including the gas pipeline that we just showed you. Okay, recent seismicity. We have a few minutes to talk about the recent seismicity. Okay, we're still working on them. We don't know much about them, other than we recorded 5 earthquakes. These are the earthquakes that they took place in central Arkansas, closely to Magnet Cove, northwest of Hot Springs. These are the series of earthquakes. The first one happened in November 1. That's 2.7. That's the largest one. And then a series of 4 over a period of less than a month. The Arkansas Department of Emergency Management borrowed a few equipment from CERI, Center for Earthquake Research and Information in Memphis, and we installed and we're still recording these things. So far, I heard there is only 1 minor earthquake that took after this series. To date, we don't have an earthquake of magnitude 2 and larger. We never had a larger magnitude in this area. Okay. Now, these are the characteristics so far of these series of earthquakes. They happen in an area that has no experience of number of earthquakes. If they happen 1 or 2, that's fine, but when we have 5 in the same area, this is very unusual. So they happen in an area that is not being known to produce large number of earthquakes. They cluster in time and space, 5 of them, in a small area, in a short period of time, less than a month. So are they hydrothermal related? We don't know yet. There also some indication, I'm going to show you the map for distribution, some indication of a linear feature, though it is possible they might be falling over a fault. The seismicity is of low-level magnitude, 2.7 to 2.0, and possibly less. Now, due to the lack of monitoring system that's in central Arkansas, the location of these events were very rough. It could be moving by several kilometers if we have a precise location. So we don't know if they are going to be close together or spaced, or they are going to align on a fault line. We don't know yet because the error in the location is still very high. The area surrounding this region have experience of hydrothermal. So it is possible they are hydrothermal related. We know the hot spring. These are the distribution of the earthquakes. This is in here, 2 on top of each other, 2.0 and 2.7, and then 2.2, 2.4, and 2.3. There is some linear feature indicates. This unknown fault, we're still working on it. We don't know exactly at this point if it is a fault zone. But so far, so good. We don't have any repetition to earthquakes in this region. So it is possibly, they might be hydrothermal related. I mean, this is in here, Malvern, that's the hot spring in here. This is the area where we do experience a lot of hot springs. The area in here is also, they have some hot springs. So it is possible, could be a hydrothermally related. Now, if they are hydrothermally related, that means the earthquake that is going to be generated from them is going to stay small. We don't anticipate to see a magnitude of 6 or 7 from hydrothermally related earthquakes. If it is going to be tectonically related earthquakes, that is going to be along a fault, that's accumulating stress, it is possible that a larger magnitude is going to be expected. But personally, I think it is not going to be tectonically related earthquake. This is just personal thoughts. We still need to do a lot of work. And I think most likely they are hydrothermally related. So it is so far so good at this point. Okay. Again, back to the same conclusion that we start with. And I'm not going to go through it because you already went through it and we're running out of time. So I'm going to leave a few minutes for any question if you may wish.
Much. Let's see, do we have questions? Let's raise some hands here. Let us get a microphone to you. Hold on just a minute. Right over here, right in the front.
Coming back to the Enola swarm and the question of periodicity, you mentioned 1981 and 2001. Was there instrumentation around that would have picked up such swarms at an earlier time, that is 1960, 1940, et cetera?
No. The monitoring system in the central United States started in 1974.
Oh.
This is the first instrument went into the ground in 1974. We didn't have any instruments before that. Yes.
Question? Right here.
Thank you for coming. All of the recent natural gas exploration in northern Arkansas with the Fayetteville Shale, would any of that production, drilling in the earth have anything to do with this, or at all, or is it entirely too shallow?
Okay, that's an excellent question. The gas and oil production, usually it's a phenomenon called induced seismicity. And induced seismicity is not just related to oil and gas production. It's related to high rise dam, changing course of a river, excavation of rocks. But one of the induced seismicity related to oil and gas production. Let me tell you what I mean by induced seismicity. We talked about hydrothermal fluid. And the hydrothermal fluid, when you have the water percolate into the subsurface and is going to lubricate the cracks, is going to move some of the partially stressed faults. This is the same phenomenon with induced seismicity, because during the drilling, you are going to inject fluid. And the fluid is going to percolate into the rocks that is partially stressed. So it is possible is going to be generating induced seismicity. Now, one of the oil companies that's requested a permit to inject back fluid, the byproduct of the fluid drilling, back into the subsurface, very deep. And the Oil and Gas Commission requested that we monitor this well. And they requested from us to design an array to monitor, and we are doing it right now. The monitor, the well, the injection well, where the fluid is going to be injected back into the ground. We put an array of 7 stations to monitor if there is any induced seismicity. So there is a relationship between oil and gas production and induced seismicity. It's usually induced seismicity is not of very large magnitude earthquakes, not like 6 or 7. They intend to be small, of maximum 3 to 4.
Got time for one more question. Got one right here in the back. Bob, right behind, yeah, right over there.
My question is twofold. The first question is, about 25 years ago, we heard a geologist at UALR say that Little Rock, sitting mainly on rock, would be not heavily impacted by a serious earthquake in New Madrid. So first, I'd like for you to comment on that. Secondly, back in the summer of last year, there was a sizable earthquake in Louisville, somewhere between 5 and 6, that knocked power out for 5 days. I know because my friend was without electricity. Can you comment on that and how that might impact what we're looking at on these faults?
Okay. The professor that you mentioned related to Little Rock sitting on a rock, this is an observation in the central United States. You have 2 types of soils. The western part of Little Rock is really sitting on rocks. The eastern part of Little Rock and the entire eastern part of the state sitting on a soft sediments. The seismic wave reaction to the soil is different than the seismic wave reaction to the rocks. The propagation within the soft sediments has the potential of amplifying the signal. That means when you have an earthquake, it generates a certain magnitude, certain amplitude of ground motion. It's going to come to the site where you have soft sediments. Because of the reverberation in the sediment back and forth, the signal will be continuously amplified. That means the severity of the ground shaking in the soft sediment is going to get higher. When it comes to rock, It's just rock. So there won't be any reverberation. So whatever is going to be generated energy is going to come. So there won't be any amplification to the signal. This does not mean the signal that is not going to be amplified is not originally strong. It is possible that, that the signal itself is strong, so it's going to affect. But it's not as much as the effect when the construction on soft sediments. I'm not recall there is any earthquake of magnitude 6. I don't know which.
Where was it? In Louisville? Louisville, Kentucky? Louisville, Kentucky.
Okay, we have a group of earthquakes that takes place in Mississippi, and I don't recall there is one in Louisville. There was one in Illinois, and one in Indiana. In southern Indiana, there was an earthquake about 5 years ago. Yes, the one in southern Indiana, western Indiana, there was a big earthquake happened about 5.2. This earthquake, and this is exactly what I said. It is possible that this is all things is part of one system.